This section introduces the central bargain of information theory. Perfect fidelity over an unreliable channel comes from adding structure at its two ends. The channel stays as noisy as it ever was. Accept the noise as given and wrap the message in an encoder and a decoder that spend redundancy to buy reliability. The whole arc of the chapter bends toward one refutation. The intuition says that vanishing error demands vanishing rate, that there is no gain without pain. That intuition is false. Shannon's boundary between the achievable and the impossible meets the rate axis at a non-zero capacity, written C. Error can be driven arbitrarily small while the rate stays fixed and positive. Reliability and speed are not conjugate. The trade-off curve does not pass through the origin. That single fact is what the whole first half of the book exists to prove. This first section explains the single move that opens the book, the claim that noise does not force a trade between reliability and speed. Noise looks like it forces a trade. To make a channel more reliable, you repeat each bit more. Buying safety with speed and perfect reliability seems to cost infinite redundancy. With the rate driven to zero, the chapter's single move is to refuse that trade. Shannon's promise, which chapter 1 stages through the binary symmetric channel and the repetition code R3, is that every channel carries a capacity. Below that capacity, there is a strictly positive rate at which the error probability can be pushed arbitrarily close to zero at finite cost. This is the generative primitive for the whole book. Reliability and rate are not conjugate quantities. Everything after, compression and coding alike, is machinery serving this one impossibility turned into possibility. This section explains how one identity generates the whole calculus of probability, entropy, and inference. A single identity generates everything here. The probability of x and y together equals the probability of x given y times the probability of y. Read it forward and you have forward probability, where a fixed model emits data. Solve the same identity for the other conditional and you have inverse probability, Bayes' theorem, which is inference in full. The chapter's thesis is that these are one rule, interrogated in two directions, not two subjects. The ensemble, written as x together with its alphabet, a sub x, and its distribution, p sub x, is merely the object the rule acts on. Entropy is those same distributions measured for spread. So you can generate any inference from here. Name a forward model, apply the product rule backward, likelihood times prior, renormalized. Nothing further is ever added. This part explains how every inference in the book reduces to a single move. The generative model runs forward, where assumptions produce data. Bayes' theorem runs it backward, from data to the belief you actually want. That inversion is the whole chapter. Joe's disease test anchor makes the stakes visible. A test that is 95% reliable, returning a positive result, yields only a 16% chance of disease because the 1% prevalence dominates. Intuition reads the likelihood and forgets the prior. Probability here quantifies degree of belief, not merely frequency. The Cox axioms license that reading. Once beliefs obey consistency, forward and inverse probability are one calculus read in two directions. Master the inversion, and every later inference in the book generates itself. This section explains why inference has a single answer rather than a menu of methods. Inference has one solution, and it is not a menu of estimators. The chapter's whole thesis lives in Steve Gull's answer to the decay length puzzle. Picture particles decaying at position, x, with characteristic length, lambda, observed only through a window. The same density, the probability of x given lambda, read as a function of the hypothesis rather than of the data, becomes the likelihood t, read as a function of the hypothesis rather. Multiplying it by a prior yields the posterior, the unique and complete answer. The generative move is that turning on its head. A distribution over data pivoted becomes a belief over hypotheses. Where orthodox statistics offers 20 estimators and 20 criteria to rank them, Chapter 3 states that Bayesian statistics only offers one answer to a well-posed problem. Make the assumptions explicit and the inference then follows, with no groping in the dark. This part explains how one Bayesian move dissolves the whole bestiary of estimators. Faced with Steve Gall's truncated decay problem, particles decaying with characteristic length, lambda, seen only through a window from 1 to 20 centimeters, the undergraduate McKay groped for sample, mean tricks and ad hoc bins. Each one worked in a single regime, none everywhere. The generative primitive is this: never invent a statistic. Write the probability of what you saw given the unknown, the probability of x given lambda, and let Bayes turn it around. The window that broke every estimator becomes a normalizing constant inside that likelihood, absorbed automatically. Every inference problem then collapses to one recipe: likelihood times prior, read off the posterior. The chapter's place in the arc is Bayes, already correct for the noisy channel, now the universal inference engine. This section explains the source coding theorem, the result that fixes entropy as the true cost of information. Start with surprise, which is logarithmic. An outcome of probability p carries log base 2 of 1 over p bits. This is the only measure that makes information additive across independent events, so learning two things costs the sum of their surprises. Average that surprise over an ensemble, and you get entropy, written H. The chapter makes a single claim. Entropy is a hard floor, not merely a convenient statistic. A stream of n independent symbols cannot be encoded in fewer than n times h bits without loss, and it needs no more than that. The mechanism underneath is concentration. Over long streams, the actual bit cost per symbol collapses onto h, so the typical outcomes become almost equiprobable, each sitting near 2 raised to the negative n times h power. Chance sharpens into a law. This section explains why entropy is the quantity it is, defined by the job it does. Entropy is the floor on bits per symbol, a number forced by operation rather than chosen for taste. Start from surprise, the logarithm of 1 over p. This is the only function of probability that adds when independent outcomes are learned together, so that the surprise of x and y jointly equals the surprise of x plus the surprise of y. Average that surprise over the whole ensemble, and you have the entropy capital X. Shannon's source coding theorem then certifies that this average is operational. A long block of n symbols concentrates almost all of its probability onto about 2 to the power n times h, nearly equiprobable typical sequences. Naming one of them costs n times h bits and no fewer. Here is the boundary that reveals the structure. The raw alphabet can be astronomically large, yet compressibility is set by entropy alone. What matters is the typical set, never the whole space. This section explains why lossless symbol coding has a conserved price and how that conservation makes compression an exercise in matching probabilities. Losslessness has a price, and the price is conserved. Encode one symbol at a time with variable, length code words, short for the probable, long for the rare, but demand that the stream decode uniquely, and every code word you shorten forces others longer. The exact conservation law is crafts. A prefix code is a tree, and its leaf depths obey a single inequality, the sum over all code words of 2 to the power of minus li is less than or equal to 1. So the quantities 2 to the power of minus li are an implicit probability distribution. Compression is then just alignment. You spend your length budget to match the true probabilities, setting each length Li equal to the base 2 logarithm of 1 over pi, which is the Shannon information content. Huffman's algorithm constructs the optimal spend, landing within 1 bit of the entropy, from h up to but not including h plus 1. Code length is currency. Entropy is the floor. This section explains why every code word length is a bet, and why optimal compression is just honest betting. Every code word you shorten forces others to grow longer, and the exchange rate is exact. Unique decodability spends from a fixed budget, the sum over all symbols of 2 to the power minus L sub I is less than or equal to 1. This is the craft inequality. Read that sum as a probability simplex and the whole chapter collapses to a single move. A code of lengths, L sub I, is a claimed distribution where Q sub I equals 2 to the power minus L sub I. Assigning a length L to a symbol bets 2 to the power minus L of your unit mass on it. Optimal compression is then just honest betting. You match Q to the true distribution P, which means setting L sub I equal to log base 2 of 1 over P sub I, the Shannon content. The price of any mismatch is the entropy gap, and that gap pins the average length into the interval from the entropy h of x up to, but not including, h of x1. This section explains stream codes and the single idea that makes them work. A string is an interval of the half-open range from 0 to 1, and its width is its probability. The number of bits needed to name that interval is the log of 1 over the width, which is Shannon's information content exactly. Now fractions of a bit become spendable because you round once for the whole stream instead of once per symbol. That single move dissolves Huffman's instead of once per symbol. The real primitive of the chapter is orthogonality. Prediction is independent of coding. The guessing game twin makes this visible. Swap the predictor, and the encoder never changes. Arithmetic coding takes the model as given, and codes almost optimally against it. Lempel and Ziv refuse to know the model and let repetition itself become the model. These are two answers to one question: where does the probability come from? This part explains why stream codes escape the defect that symbol codes cannot. A symbol code assigns each symbol its own whole number of bits. That integer rounding is the flaw. Huffman cannot escape, as Chapter 5 shows. Stream codes dissolve the boundary between symbol and code word. The entire message becomes one number. Arithmetic coding is the clean form. The model's predictive distribution nests the interval from 0 up to but not including 1, recursively. Each symbol carves out a subinterval whose length is exactly its conditional probability. So the final interval's length is the message's probability, and the bits naming it are precisely the negative logarithm, base 2 of p. No rounding, no code table, but why no rounding, no code table? The compression is the model, cleanly separated from the arithmetic. Decoding replays an identical predictive twin, Lempel. Ziv takes the opposite bet, one universal algorithm, model-free, learning redundancy from the stream itself. This section explains why every way of coding an integer is secretly a probability prior. Every way of writing an integer as bits quietly declares how surprised you expect to be by its size. A code is a pariah in disguise. Craft ties the two together. A code word of length, L of n reserves probability 2 to the power of minus L of n. So choosing the lengths is the very same act as choosing the distribution, P of n. Unary spends in bits, so it believes that P of n equals 2 to the power of minus n. The self-delimiting family, C alpha, C beta, and onward to Elias's C omega, recurses on one idea: encode the length of the length in order to bet on ever larger integers. This dissolves the question the chapter refuses to answer. No code is best. Any complete code corresponds to a prior for which it is optimal, so superiority is only ever relative to which integers you expect. Pick the belief, and the bits follow. This part explains why encoding an integer is secretly a wager on how large integers tend to be. Encoding an integer forces a prior on the integers. A code word of length, L declares a belief that the probability of n equals 2 raised to the power of minus L of n. So every complete code is an optimal code for exactly one distribution. None is universally superior. They differ only in which sizes they bet on. The generative move is self-reference under the pun that a length is itself an integer. To send n, you first send the bit length of n, its own number of bits. But that too needs a code, so you send its length and you iterate. Unary, then C alpha, then C beta, then Elias's C omega. Is that recursion taken to its fixed point, each layer naming how long the next name is? Given any object of unknown extent, you can now derive its self-delimiting code yourself. This section explains why correlation is exactly the failure of entropy to add, and how mutual information measures that shortfall. Correlation is the failure of entropy to be additive, and mutual information measures exactly the shortfall. When two variables are independent, the joint entropy of x and y equals the introsed of x plus the entropy of y. Couple them, and the joint uncertainty drops by the mutual information between x and y, which is the Kullback-Leibler divergence of the true joint distribution from the product of the marginals. That is the KL distance from the product that independence would have imposed. One identity generates the whole chapter. The joint entropy of x and y equals the entropy of x plus the conditional entropy of y given x. This is the chain rule. Figure 8.1, which partitions the joint entropy into marginal, conditional, and mutual pieces, is pure bookkeeping over that one identity. And this is the machinery McKay builds it for. A noisy channel is nothing but a correlated joint ensemble of input and output, so the entropy of coupled variables becomes the very language of communication, carried forward in chapters 9 to 11. This section explains why mutual information is the single meter this chapter installs, and why the whole entropy diagram is one identity in disguise. Correlation is just distance from independence, and this chapter installs the 1 meter that reads it, mutual information. The mutual information measures how far the real joint departs from it. Is the Kullback-Leibler divergence of the true joint distribution P of x and y from the product of the marginals P of x times P of y. That product is the separable model the compression chapters assumed, and mutual information measures how far the real joint departs from it. Everything else on McKay's entropy diagram, figure 8.1, is a single identity seen from different sides. The chain rule says the joint entropy of x and y equals the entropy of x plus the conditional entropy of y given x. The mutual information is the overlap in that picture, the region where the two marginals double count. The step that makes the chapter matter to the arc, the reason it exists at all, is that a noisy channel is a correlated ensemble. Were the input and output independent, the mutual information would be zero and communication would be impossible. Chapters 9 through 11 are already written here, in the entropy of joint ensembles. This section explains why the cost of a noisy channel is measured by uncertainty and how that leads to a single number called capacity. Start with the naive move that fails. Suppose you flip 10% of 1,000 bits. It is tempting to subtract and say you have lost 100 bits of rate. That subtraction is wrong because the receiver cannot locate which bits were flipped. The right measure of what the channel costs you is uncertainty, not the raw count of errors. The honest measure is mutual information, written as the mutual information between the input X and the output Y. It equals the entropy of X minus the conditional entropy of X given Y. Read that as how much seeing the output collapses the uncertainty about the input. But that quantity depends on what you feed in. Maximize it over all input distributions, and the dependence on your choice dissolves, leaving an invariant of the channel alone. That invariant is its capacity, written C of Q. At this point, the channel stops being a thing that corrupts and becomes a single number, the ceiling on reliable throughput. Every model you meet here, the symmetric channel, the erasure channel, the Z channel, and the noisy typewriter, is an anchor for computing that one quantity. This section explains why the amount a noisy channel carries is a drop in the receiver's uncertainty, not a count of surviving symbols. Ask how much a noisy channel carries, and the tempting answer, bit sent minus expected errors, is wrong. The receiver never learns where the flips landed. So at f equals 0.5, half the symbols arrive correct by chance, yet nothing crosses. What actually crosses is the receiver's drop in uncertainty about the source, the mutual information. The mutual information I of X and Y equals the entropy of X minus the conditional entropy of X given Y. Conditioning is not monotone. A particular Y can raise uncertainty, so the entropy of X given Y equals 3 can exceed the entropy of X. But averaged, it never does, and that average gap is the throughput. Its maximum over input distributions is the capacity, C, a strictly positive rate below which error can be driven arbitrarily small. Reliability is bought by spending rate, not by counting mistakes. This section explains the noisy channel coding theorem. The single wall, that noise sets on communication. Noise does not force you to trade speed for reliability. It sets a single wall. That wall is the capacity, written C, the maximum mutual information the channel permits between its input and its output. Below the wall, at any rate, R less than C, the error probability can be driven arbitrarily close to 0. The structural move McKay makes is that reliability comes from coding over long blocks rather than from slowing down. A random codebook, decoded by typicality, succeeds with a probability approaching 1. The primitive to carry is this. A channel collapses to one invariant number, and that number partitions all rates into the achievable and the impossible. Every converse follows from the partition. This section explains why channel capacity is a promise rather than a bound, and it explains the proof shape that delivers that promise. Capacity stops being a mere upper limit and becomes a promise. Below capacity, C, you can drive the block error as low as you like. Above the rate, C, divided by 1 minus H2 of P sub B, you cannot. The channel has a sharp reliability frontier, a cliff rather than a gentle slope. The chapter's real gift is the shape of the proof. The number matters less. To show that one good code exists among an astronomically large set, Shannon never builds it. He averages the error over a random ensemble of codes, shows that the mean vanishes as n grows large, and concludes that a below-average code must therefore exist. The name for this is the probabilistic method, existence proven by expectation. Jointly, typical sequences are simply the counting tool that makes the average computable. This section explains how a continuous channel is really just a discrete one wearing coordinates. That is the whole chapter, and its job in the book's arc is to cache Shannon's existence proof, established for discrete channels, into the real, analog channels physics hands you. The move is this. Project any band-limited signal of duration t onto orthonormal basis functions, and it collapses to exactly 2wt, real numbers, each an independent scalar corrupted by additive Gaussian noise. So a bandwidth, w, power p, noise n naught, physical channel, is the discrete time Gaussian channel, used 2w times per second. Continuity was never the obstacle. It dissolves into finitely many independent scalar channels, and the theory you already have transfers untouched. There is a boundary. The same trick sets up, without a power cost, one transmission carries infinite information. This section explains how the coding theorem for real physical channels is won by a change of basis rather than a fresh proof. Reality here is a change of basis away from a theorem already proved. The noisy channel coding theorem lives on discrete channels, yet physical channels are continuous in time and in amplitude. So the chapter's single move is to collapse the continuous case onto the discrete one rather than rederive anything. Project a band, limited signal of duration t, onto orthonormal functions, and the channel factors into n independent uses of one scalar Gaussian channel, where n equals 2 times w times t. That scalar channel is y equals x plus n. Bandwidth and power become a use, rate and a per-use variance. The infinities of the real line are disciplined by a single quadratic cost constraint. What Shannon guarantees for the discrete world, therefore, transfers intact. Only the coordinates changed. The content stayed the same. This section explains why retrieval is a mapping between bit string sizes and how hashing makes the intractable version cheap. Retrieval is an inverse mapping problem. Given a name string, return its record number. The lookup table solves it in one step, but it needs a slot for every possible string, 2 to the 200th power of them, more than the particles in the solar system. Hashing's move is to collapse the domain first. A pseudo-random function projects each n-bit string down to a short m-bit address, where m is much greater than the base, 2 logarithm of s, yet still vastly below n. The table now fits, and the one-step lookup returns. The generative primitive is that retrieval is just a mapping between bit string dimensionalities, the same object as source and channel coding. The intractable version becomes cheap the instant you accept a lossy projection, and you pay for it by resolving the collisions that the loss creates. This part explains how retrieval works when you invert a map and cannot afford the exact solution. Retrieval is inversion. You hold the map from record to name, and what you want is the map from name to record. The exact solution is a lookup table indexed by the name itself. It is perfect and impossible because it needs 2 to the 200th power cells for a 200-bit key. The move is to shrink the key first. A pseudo-random map H takes n bits down to m bits, where m is about the log base 2 of s. This projects the vast, near-empty string space onto a table barely larger than the population you actually store. Now, the dumb table you just rejected becomes feasible. You buy that tractability with collisions. Distinct names collide into one cell, and that ambiguity is handled downstream. The generative primitive is this. An infeasible exact method becomes feasible by projecting to a space sized to what you actually store, paying for it in ambiguity. It is the same. N-bits becomes M-bits gesture as source and channel coding, only now it is compressive. This section explains why a code's minimum distance is the wrong thing to maximize. A code's minimum distance, written D, certifies a guarantee. It lets you correct any error pattern of weight up to T, where T is the floor of D minus 1, all divided by 2. The reason is geometric. The spheres of radius T drawn around distinct code words stay disjoint, so no received word falls inside 2 of them. Coding theory then chases D. Bigger guaranteed falls inside 2 of them. Coding theory then. The chapter's thesis kills that reflex. Maximizing a worst-case guarantee is the wrong objective because the channel almost never hands you the worst case. A bounded distance decoder, one that refuses to decode beyond T errors, cannot reach the Shannon limit. Only decoders that routinely correct more than T errors can reach it. McKay names the disease. He calls it worst-case-ism, a widespread mental ailment which this book is intended to cure. The generative primitive is this. Optimizing the guaranteed floor sacrifices the typical case performance that actually matters. Good codes need not have good distance. This section explains why coding theory's fixation on minimum distance is the wrong target, following McKay's argument. Coding theory fixates on minimum distance, written D, because a code guarantees correcting the floor of D minus 1 over 2, a count called T. That count is the radius of a sphere drawn around each code word, sized so it touches no other code word. McKay's chapter is a polemic against that fixation, which he names worst case is a polemic. The guarantee is real, but it is the wrong invariant to maximize. Certainty on the worst error pattern is bought by discarding the typical one. In high dimensions, almost all of Hamming space lies between the spheres, not inside them, so a bounded distance decoder that refuses to guess out there throws away nearly everything, and provably cannot reach the Shannon limit. Perfect codes, the ones that tile space exactly, would vindicate distance as the right target. But they barely exist. This section explains why very good linear codes must exist, and it proves this by averaging rather than by construction. The whole move is to bound the mean error over an entire ensemble of codes, and never to build a single code by hand. If that average error vanishes, then almost every member of the ensemble must be good too. That one idea is the entire chapter. Here is the mechanism. The typical set decoder fails only when a second typical noise vector happens to share the true vector syndrome. Average over random parity check matrices exactly when the rate R is less than 1, minus H2 of F, FF, FF2 of F, 2 to the power minus M. So the total error is at most the size of the typical set times 2 to the power minus m, which is approximately 2 to the power minus m, which is approximately 2 to the power n times f. This quantity vanishes exactly when the rate r is less than 1 minus m dt. Now, the surprise. The very same inequality is both theorems at once. Syndrome decoding is uncompression. So the statement that very good codes exist and the statement that compression down to the entropy exists are one single counting fact, the size of the typical set weighed against the size of the syndrome space. This is the probabilistic method. The ensemble average certifies the existence of an individual code that it never actually names. This part explains how one averaging calculation forces both of Shannon's theorems out at once. You take a single calculation, averaged over the whole ensemble of random parity, check matrices, and both theorems fall out together. You never build a good code. You show instead that the mean error probability over all linear codes vanishes once the entropy of X is less than m over n, so at least one code must beat the mean. This is the probabilistic method. You prove that a member with property P exists by showing the ensemble average has property P. The same syndrome decoding calculation reads two ways, as noisy channel decoding and as lossless compression of a redundant source, so the one bound yields the source coding theorem too. Here is the surprise. Almost all linear codes are very good. The rare object is the bad one. This section explains why Chapter 15 adds no new information theory and instead turns the counting bound into something you perform by hand. Every puzzle here is one move: the two-dice questioning, drawing straws from a coin, Esmeralda naming the hidden card, the ISBN check digit, each is the same gesture. You count the distinguishable configurations your medium affords, you weigh them against the entropy you must convey, and the scheme exists if and only if the first number covers the second. Take the magician's 5 ordered cards. They carry the base, 2 logarithm of 5 factorial, which is about 6.9 bits, and that is enough to name a number from 1 to 100. The mod 11 check digit is a syndrome sized exactly to catch any single slip or any adjacent transposition, no more and no less. Shannon's theorems promised that the bound is reachable in the block limit. Here you reach it by hand, exactly, at 0 error, once per puzzle. This section explains the surprise that a textbook chapter tucks away inside its exercises. 2 encoders that cannot see each other's data still hit the joint bound as if they had colluded. That is the whole surprise. The chapter smuggles in under the word exercises McKay's own signpost that the most exciting exercises are towards the end marks the pivot from rehearsal to result. Exercises 15.1 through 15.16 drill, chapters 1 through 14, the tail, Slepian Wolf, correlated sources, multiple access, broadcast, and two-way channels shatters the single sender frame that owned every prior chapter. Put several parties on one channel, and achievability stops being a number and becomes a region, a polytope whose facets are conditional entropies. Correlation need never be transmitted. Each source coded blindly at its conditional rate suffices, and the receiver still reconstructs the joint. This section explains how a global quantity can compute itself from purely local exchange, and the one property of the graph that makes it possible. A global quantity computes itself from purely local exchange the moment the graph is a tree. McKay's soldiers in the mist make it concrete. No soldier sees the line, yet each adds 1 to a neighbor's number and the total falls out. This works because any point splits a line into front and behind, 2 counts computed independently and then summed. That is the whole primitive separation. A node in a tree carves the rest of the graph into disjoint subtrees that share no information except through it, so a global sum factors into local ones. The swarm of gorillas breaks exactly when a cycle lets a node fail to separate. Jim cannot say who is in front. Tree implies separable, and separable implies that local suffices. This section explains how a global quantity that seems to demand seeing everything at once, total soldiers, number of paths, cheapest route, collapses to local arithmetic the moment it separates. Whenever the graph has a cut that splits the whole into independent pieces, each side computes its share blind to the other, and a node just computes its share blind to the other, and a node just combines what arrives. That is the entire chapter. The soldiers in the mist counting trick, sum product path, counting, and min sum shortest path, which is Viterbi, are one algorithm read over different operations, add and combine, sum and multiply, min and add. Separability is the precondition. A tree, meaning a graph with no cycles, is what guarantees a clean cut at every node. There is no enumeration ever. The fold is the answer. This section explains how a constraint on the strings a channel can carry turns into an eigenvalue problem. A constraint on which strings a channel admits is a graph, its states, and the transitions the rules permit. Counting the valid messages of length n is then counting walks of length n, which are the powers of that graph's adjacency matrix. Their number grows as lambda to the n, for the dominant Perron eigenvalue, lambda. Width. So the capacity is exactly the base 2 logarithm of lambda. That is the whole chapter, a run-length rule phrased as forbidden substrings across channels A, B, and C becomes an eigenvalue problem. The best code drives the channel with the symbol frequencies that its leading eigenvector prescribes. The move that makes this work is the one from chapter 16, a global count extracted from purely local structure, the constraint's own transfer operator diagonalized. This section explains why the capacity of a constrained channel is an eigenvalue. Forbid certain substrings. In channel A, everyone must be followed by a 0, and the count of legal strings of length n stops doubling. It grows like lambda to the nth power, where lambda is the largest eigenvalue of the channel's connection matrix, the adjacency graph of permitted state transitions. Channel A's counts run Fibonacci, so lambda is the golden ratio and the capacity is the base, 2 logarithm of phi, approximately 0.69 bits per use. The whole question, how many bits per channel use, collapses to how fast the set of permitted words grows, and matrix powers answer that through their spectral radius. A constraint is a graph. Counting paths through it is the capacity. A transfer matrix, Perron, Frobenius situation. This section explains why building a crossword and cracking a cipher are the same piece of arithmetic. One currency underwrites the whole random walk, log probability. That a language admits many crosswords measures its redundancy. A filled grid is a constrained channel whose capacity stays positive only when the dictionary is rich relative to the alphabet's raw entropy. So the mere existence of crosswords sets a lower bound on how far English falls short of gibberish. Run the same ledger the other way, and it breaks enigma. Turing's codebreakers summed weights of evidence, log odds counted in decibunds, until the tally crossed the roughly 129 needed to overwhelm 8 times 10 to the 12th candidate machine states. Building a crossword and cracking a cipher are one arithmetic. Both are probabilities of data under competing constraints, added in log space. Language questions are entropy bookkeeping. This section explains why the existence of crosswords is a measurement of a language rather than a pastime. That a language admits crosswords at all is a measurement. McKay's move is to read the crossword grid as a constrained channel in chapter 17, where each filled square must satisfy every word crossing it. Whether arbitrarily large valid grids exist depends on one number, the entropy per character of word, English. Too much redundancy, and every random filling collides with the dictionary. Too little, and any scribble is valid. Crosswords live in the narrow band where the entropy of word, English, clears the type A and type B thresholds, so their mere existence bounds language, redundancy from below. The whole chapter is this one inversion applied twice, first to crosswords, then to code breaking. Redundancy is what a puzzle silently quantifies. This section explains why sexual reproduction exists, framed as a question about the rate at which a genome absorbs information from natural selection. Natural selection is a channel whose entire teaching signal is at most 1 bit per offspring, survived or did not, and it is hugely redundant since unfit individuals fail for the same reasons. The chapter asks the rate question: how fast does a genome of G bits absorb those bits? A crude linear fitness model answers by mode of variation. Asexual reproduction corrects defects serially, giving Maynard-Smith's rate of about 1 bit per generation. Sex recombines the independently good bits scattered across the whole population, letting truncation selection act on many at once, so acquisition scales as the square root of G per generation. Same channel, same signal. Recombination merely parallelizes what mutation captures 1 bit at a time. That parallel information pump is why sex exists. This section explains why selection behaves like an information channel and why sexual reproduction changes how fast that channel fills. Selection is a channel, and the question is its capacity per generation. Fitness here is just a bit sum over the genome, so evolution's job is flipping bad bits to good, acquiring bits about the environment. Under asexual mutation, the teaching signal stays redundant. The population corrects the same defects in parallel, so information arrives at order 1 bit per generation regardless of population size, which is Maynard-Smith's figure. Recombination breaks that redundancy. A child samples independently across loci, and the rate jumps to order the square root of G. Same selection pressure, same genome, the variation operator alone changes the exponent. That gap is the answer to the question of why sex. This section introduces inference through the example of clustering. Grouping N points into K clusters is the chapter's chosen vehicle for that idea, and the word example in the title is the tell. The task is only scaffolding, a vehicle that carries you toward inference rather than the destination itself. K-means is its crudest instantiation. You initialize K-means, then iterate 2 steps until they reach a fixed point. The first step is assignment. Each point claims its nearest mean. The second step is update. Each mean slides to the average of the points that claimed it. The clusters compete to own the data. The one primitive to carry forward is this. K means is coordinate ascent that minimizes a distortion, and the hard nearest mean choice is a collapsed stand-in for a posterior probability. It is a lossy shortcut, and the book stages it here precisely so that it can later be softened into genuine probabilistic inference. This section explains how the chapter stages clustering as an inference problem. Clustering enters as an inference task rather than a recipe. The whole move of the chapter is to present K means as a plausible ad hoc algorithm, and then let its failures name what it silently leaves out. The algorithm runs in 3 steps. Assign each point to the nearest mean. Move each mean to the points it owns. Iterate until you reach a fixed point. What you are watching is a competitive scramble for ownership. Then, 2 anchors show the crack. The first is a cluster with few points beside a cluster with many, the little n against the large N. The second is an elongated cluster. In both, the distance metric sees only distance, so the algorithm carries no representation of a cluster's weight, its breadth, or its shape. Its hard assignment also lets no point half belong to two clusters. Here is the structural primitive to keep. An algorithm's failure modes are the coordinates of the generative model. It refuses to write down. This chapter builds the demand. The probabilistic mixture is what answers it. This section explains exact inference by complete enumeration, the honest starting point of Bayesian methods. Bayesian inference collapses to a single move. List every hypothesis. Weight each one by prior times likelihood, then normalize. Enumeration is that move taken literally, with no approximation and no cleverness, just the sum written out. Mackay opens the toolbox here because this is the honest 0 point against which every later method is measured. It is exact and therefore doomed. The burglar and earthquake anchor hands you the surprise that reorganizes your model. Two causes that are independent a priori become coupled once you condition on their shared effect. This is explaining away, and because of it, the posterior never factorizes. The failure is quantitative. A grid over k parameters costs 10 to the kth power. That exponential wall is the chapter's real payload. It defines the problem that every following chapter exists to evade. This section walks through inference reduced to its most honest form. List every hypothesis, weight each one by Bayes, then sum away whatever you don't care about. That is the whole method. The posterior is a table you fill in cell by cell, and marginalization is just adding columns. Mackay's burglar alarm anchor shows the one structural surprise this brute force makes visible, explaining away. Burglar and earthquake are independent, a priori, and they become coupled once the alarm is observed because conditioning on a shared effect ties its causes together. The chapter is a baseline that indicts itself. Exactness costs a grid of 10 to the kth power points, one factor of 10 per parameter, so the cost detonates with dimension. Every later method exists to buy that same posterior without paying the enumeration. This section explains maximum likelihood and clustering and why the two turn out to be the same procedure. Enumerating every hypothesis costs exponentially. Maximum likelihood trades that sum for a climb. Instead of integrating over all parameter vectors, you find the single vector theta that maximizes the probability of the data given theta. When the model is simple, the peak is closed form. The data enter only through sufficient statistics. For one Gaussian, those are the sample mean and the sum of squares, so the estimate reads straight off them. When the model hides a latent label, meaning which Gaussian generated each point, no closed form exists. The combinatorial question of which point belongs to which cluster dissolves into a fixed point loop. That loop alternates soft responsibilities against re-estimated parameters. That loop is clustering. Soft k-means is this expectation. Maximization, iteration, wearing a different name, the unsupervised fitting of a mixture. This part walks through what maximum likelihood does and why it is a single move. Where? Chapter 21, integrated over hypothesis, chapter collapses the whole posterior onto its peak, the single theta that maximizes the probability of the data given theta, the generative primitive is its substitution, replace the intractable sum over hypothesis, spaced with a search for one point. Because data points multiply their probabilities, you climb log likelihood instead. Likelihoods multiply, log likelihoods add. which turns a product into a sum you can differentiate. The Gaussian falls out instantly, its mean and variance read straight off the sufficient statistics. A mixture of Gaussians does not, and the same peak finding, now applied to hidden assignments, becomes clustering. Predict the sequel. Whenever the maximum has no closed form, you iterate, soft assign, and re-estimate, which is EM. This section explains how a catalog of probability distributions is really one lookup table indexed by structure. Every entry answers a single question. Given the support of a quantity, what is the natural law over it? A count wants the binomial or the Poisson. A positive scale wants the gamma. A proportion wants the beta. A direction wants the von Mises. Support fixes the family. A secondile, tail weight, fixes the member. Mackay's recurring warning is that the Gaussian's tails are too light to trust, so the student becomes the honest default once outliers are possible. Read this way: the chapter is a lookup indexed by structure. You generate the right prior from what the variable is, whether count, scale, proportion, or angle, rather than memorizing a bestiary. This section catalogs the useful probability distributions and shows how to choose among them. The catalog organizes them by the support of the variable they live on, the integers, the unbounded reals, the positive reals, periodic angles, and probabilities on a simplex. You pick one by matching that domain, never by memorizing. As Mackay puts it, only the Gaussian earns memorization, and it memorizes itself. The chapter's real surprise is his warning against the reflex reach for that Gaussian. Its tails are extremely light. A 5 sigma event sits at 6 times 10 to the minus 7, so a misfit contorts the whole model, like a sheet of paper crushed by a rubber band. And a density's apparent pathology, a spike at 0, is an artifact of coordinates. We parameterize to log x, the logit, the softmax, and the ugliness dissolves. Choice of basis carries the content. This section explains exact marginalization, the 24th structural primitive. A question picks the variables you keep. Every other variable you don't estimate, you sum away. Marginalization is the joint distribution projected onto the axis you asked about, and the chapter's claim is that this projection is often exactly doable, dodging the exponential enumeration of all hypotheses. The anchor is the calculator's 2 buttons. Sigma sub n maximizes sigma with the mean held fixed. Sigma sub n minus 1 is what marginalizing the mean away leaves. The n minus 1 is the single dimension of noise. The Occam factor eats once. One parameter is integrated out. Exact only where the sum closes. Conjugate integrals over continuous nuisance parameters. Message passing over discrete ones. This part explains why the 2 standard deviation buttons on a calculator are the same object seen twice, and how marginalization is the engine underneath them. Marginalization is the whole engine. To answer what is sigma, never mind mu, you integrate the unwanted parameter away, and the answer is a distribution, not an estimate. The chapter's compression is this. The frequentist 2 calculator buttons, sigma sub n and sigma sub n minus 1, are not rival hand-built recipes. They are the same posterior seen twice. Sigma sub n is its peak with mu pinned. Sigma sub n minus 1 is its peak after mu is summed out. The famous n-1 is not a correction rule bolted on. It is exactly what integrating out mu costs you one noise dimension eaten by fitting the mean, surfacing as an Occam factor. Turn the handle of probability and the ad hoc estimators fall out as shadows. This section gives the thesis of exact marginalization in trellises as a single structural primitive. The move that does the work is this. The trellis converts a code's global constraint into a chain, and marginalization or maximization factors along that chain. A code's exponential set of code words hides a linear skeleton. Draw every code word as a path through a layered graph, the trellis, where each edge emits one bit and the width at any time is bounded by the number of distinct partial syndrome states, not by the number of paths. Once the answer you want, which code word or how likely bit n is a 1, is a sum or a max over all paths, and the channel's likelihood factors edge by edge. That sum distributes across the layers. You sweep left accumulating, you sweep right accumulating, and you combine. These are the forward, backward, and min-sum algorithms. The primitive is this. Decoding is marginalization, and marginalization over a chain is a two-pass local recursion. Exponential enumeration collapses to linear in trellis length whenever the global object admits a state-bounded sequential description. This section explains how brute force decoding over an exponential set of code words collapses into a walk along a graph. A brute sum over 2 to the k code words collapses to a walk along a graph the moment the code's constraints factor into a chain, the trellis, where every left to right path is one code word. Marginalization becomes accumulation. A message at each node folds in everything to its left, so cost grows with edges, not paths. The step that carries the whole argument is that two decoding questions are the same computation under different arithmetic. You can maximize the single best path, which is min-sum Viterbi, the map code word, or you can sum all paths through each bit, which is sum product, forward, backward, BCJR, the bitwise marginals. The two are separated only by swapping the min plus semi-ring. The two are separated only by swapping the min plus semi-ring for the plus times semi-ring. Distribute a sum of products over a linear factorization and the exponential disappears. The semi-ring you choose decides which inference you get. This section explains exact marginalization in graphs. The starting point is one shape that every inference task the book has been circling reduces to, a product of factors summed over its variables. To normalize, you sum out everything to get the constant z. To marginalize, you sum out all but one variable to get z sub n of x sub n of x sub n of x sub n. The chapter's move is to stop treating the target distribution, p star of x, written as the product over m of the factors f sub m of x sub m, as a monolith, and instead read its factorization as a graph, with variables and factors wired together by shared dependence, as drawn in figure 26.1. Once the factorization is drawn, the summation is no longer flat. A sum over some variable x sub n prime commutes past every factor that does not touch it. That is the whole primitive. Exact marginalization is the distributive law made structural. The sum of a times b equals a times the sum of b, pushed as deep into the product as the graph allows. The repetition code posterior is the anchor here, and here is what survives to the next chapter, on a tree. This collapses to local messages. This section explains why summing over a tree-shaped factor graph is cheap, and why the very same procedure computes more than one thing. Summing a product of m factors over all joint settings costs exponentially. Yet, whenever the factor graph is a tree, that cost collapses to linear. The generative primitive is the distributive law. A sum of products factors into a product of sums, so the global marginal decomposes into local messages, each edge carrying one function of one variable, computed only from its neighbor's incoming messages, incoming messages, incoming messages. Marginalization is message passing along the tree. The answer at a node is the product of everything flowing in. The deeper compression is that nothing depends on the operations being addition and multiplication. Swap the semi-ring for maximization and multiplication, and the same machine finds the most probable configuration, the Viterbi decoder, instead of the marginal. This section explains Laplace's method, the trick that answers an intractable integral by looking at a single point. The idea starts from one observation. A sharply peaked density contributes almost nothing away from its maximum, so the curvature at the peak carries the whole story. Expand the log of p star to second order in a Taylor series, and the integrand becomes a Gaussian, whose normalizing constant you already know. From this, the total mass z sub p collapses to peak height times a determinant. It equals p star at the point x0 times the square root of 2 pi to the k, divided by the determinant of a, where a is the Hessian of minus the log of p star. The shape of the move is the payoff. A global question about total probability reduces to two local measurements, where the top is and how fast it curves down. The primitive generalizes to any Laplace-type integral, any integral of e to the m times g of x. The physicist's saddle point approximation is the same move. There is one catch. The method lives in your chosen coordinates, so the answer is basis dependent. This section explains Laplace's method, the trick that turns an intractable integral into a Gaussian you already know how to normalize. Any integral you cannot do becomes one you can, if you are willing to believe the integrand is a Gaussian. Laplace's method locates the peak x0 of an unnormalized density. Taylor expands its logarithm to second order, and because the linear term vanishes at a maximum, what remains is pure curvature. From there, you read off the one normalizing constant everyone knows. A Gaussian's is pure curvature. From there, you read off the one normalizing constant everyone knows. A Gaussian is on an unnormalized density. The Hessian of the negative log of p star sets the width. The square root of 2 pi to the k over the determinant of a replaces the intractable normalizer, z. The generative move is this. Near a peak, everything is locally quadratic in log space, so second-order truncation is the smallest surrender that still integrates in closed form. The catch that predicts every failure is that the method is basis-dependent. Reparametrize non-linearly, and z sub q shifts, defect, and lever at once. This part explains why Occam's razor needs no separate axiom, because it falls out of normalization. Each model's evidence, the probability of the data given the hypothesis, is a probability distribution over the space of possible datasets, so its total mass is fixed at 1. A model flexible enough to predict many datasets must spread that unit budget thin. E9, model flexible enough to anyone. When the data land where both models reach, the simple one, having bet its whole budget on a narrow region, scores higher automatically. The Occam factor is just this conservation. Predictive breadth is paid for in per outcome probability. McKay's cubic versus add4 sequence makes it concrete 40 million to 1 purely from the flexible theory diluting itself with no aesthetic prior invoked. This section explains why the simplest model that fits the data tends to win, and how that preference falls out of probability alone. A model's evidence, the probability of the data given the hypothesis, is a normalized distribution over the space of possible datasets. Its total probability mass is fixed. A complex model reaches more datasets, so it spreads that same mass thinner. Predicting broadly means predicting each individual outcome only faintly. When the data fit both models, the simpler one concentrates its mass where the data actually landed, and it wins by arithmetic alone. Occam's razor then needs no added penalty term for complexity. It falls out of normalization directly. McKay's chapter turns the aesthetic preference for simplicity into a computed odds ratio, 40 million to 1 in favor of the rule. Add 4 over the cubic model on the sequence, -1, 3, 7, 11. This is the second level of inference, model comparison, and here the conserved mass argument is the whole of the razor. This section explains why Monte Carlo methods reduce to a single operation. Every expectation you actually want, a mean, a variance, a marginal, is an integral against p of x, and an integral against p of x is just the average of samples drawn from p. So the entire subject collapses to one verb, sample. Estimation is a free corollary of sampling. The hard problem was never the arithmetic. Sampling is hard for one structural reason McKay keeps returning to. In high dimensions, the probability mass lives in a typical set, a vanishing sliver of the space, and you know P only up to its normalizer. Every method downstream, rejection, importance, metropolis, is machinery for reaching that sliver blind. This part explains why the whole problem reduces to a single hard move. Sampling. Everything reduces to one move. Draw samples from P of X when you can only evaluate it up to its normalizer. Expectations, moments, variances all become sample averages once you have the samples, and the estimate's accuracy rides on the variance of phi, not on dimension. So the whole difficulty concentrates in sampling itself. The obstruction is structural. Probability mass hides in a typical set whose volume is a vanishing fraction, 2 to the power h minus n of the space. So uniform enumeration must implicitly discover the canyons, finding where P is large without evaluating it everywhere. McKay's lake with a plumb line is the whole chapter. Locate the deep water blind. Every later method is a strategy for that search. This section explains what makes every sampler in the chapter fast. And it is a single enemy, the random walk. Vanilla Metropolis explores by diffusion, decorrelating across a distance. L therefore costs about L over epsilon squared steps. That is the square root of t crawl of Brownian motion, where displacement grows only as the square root of time. Each trick in the chapter buys ballistic motion instead, displacement that is linear in time. Hamiltonian Monte Carlo is the cleanest instance. You augment the state x with the momentum variable p, then let Hamiltonian dynamics carry the state persistently along its trajectory instead of re-randomizing at each step. The walk becomes a glide, costing only L over epsilon steps, a quadratic speedup. Over-relaxation and Skilling's leapfrog are the same move reclothed. Each one suppresses the backtracking that makes diffusion slow. The chapter's primitive is this. This section explains the single move that unifies every sampler in this chapter. Every sampler here fights one enemy, the random walk, whose state wanders a distance growing only as the square root of t, so decorrelation is quadratically slow. The move that unifies the chapter is persistence. Break the diffusive symmetry so that successive steps stay correlated in direction, and distance covered grows linearly in direction, and distance covered grows linearly in direction, and distance covered grows linearly in t instead. Hamiltonian Monte Carlo buys this with momentum. A particle coasting downhill on E of x keeps its heading. Over-relaxation buys the same thing with a deliberately non-reversible chain, biasing each Gibbs draw toward the far side of the conditional. Different machinery? One primitive. Ballistic beats diffusive. Now you can predict the rest. Any trick that makes exploration directed rather than aimless belongs here. This section explains the sense in which a magnet is a probability distribution. Put a spin of plus or minus 1 on each lattice site. Let neighbors prefer alignment through a coupling J under a field H. The Boltzmann weight, the exponential of minus beta times the energy, taken over the 2 to the n configurations, is a joint distribution over binary variables. That fixes the chapter's place in the book. The Ising model is the test bed where the sampling and inference machinery built earlier meets a system that fights back. Near the critical temperature, correlations span the whole lattice. The partition function resists exact evaluation, and Monte Carlo mixing crawls. Physics hands inference, a hard case with a known answer. The phase transition becomes a statement about inference, difficulty, not only about matter. This section explains why one toy lattice of spins turns out to be the same object as memory and inference. Start with the generator, a lattice of plus or minus 1 spins, each paying an energy penalty for disagreeing with its neighbors. That single local rule, summed over the edges, is the whole generative program. From it, the chapter draws its thesis. Collective order is a consequence of purely local coupling. And the same energy, the energy equals minus 1/2 the sum over pairs of the coupling, Jmn times xm times xn me, becomes something else entirely when you let the couplings vary. A spin glass, a Hopfield network, a Boltzmann machine are one chassis under 3 names. The payoff is universality. Any system sharing dimension and symmetry shares critical exponents, so one toy lattice reports on phase transitions everywhere. Magnetism, associative memory, and probabilistic inference turn out to be the same object viewed through different couplings. This section explains exact Monte Carlo sampling, the Prop and Wilson construction that certifies a draw instead of assuming it. Ordinary Markov chain. Monte Carlo hands you a sample from the target distribution only as time goes to infinity. You assume convergence. You never certify it. Prop and Wilson's move is to run the chains from the past rather than into the future. Instantiate a copy in every state at time, negative t, drive them all with one shared stream of randomness and watch. If by time 0 they have coalesced to a single state, that state is an exact draw. The output no longer remembers which start produced it, so the initial condition has been erased. Coalescence is convergence, you can see. Stopping forward would bias the result. Only the from, the past construction, is unbiased. The chapter's whole thesis is this: certify the sample, do not pray for it. This section explains how Prop and Wilson turn the question of Markov chain convergence into something you can actually detect. Every Markov chain forgets where it started, but you never know when, and that ignorance is the defect in all Markov chain. Monte Carlo. Run the chain too short and you sample some other distribution. Call it P at time T, not the true target, P. There is no honest way to ask, from the inside, has it converged yet? Prop and Wilson. In chapter 32, convert that unanswerable question into a detectable event. Couple chains started from every state through one shared random number stream. Where 2 trajectories meet, they fuse forever, and once fused, they can never separate. Now run them forward from far enough in the past, up to the present. If all of them have coalesced by the present moment, then that present state is provably an exact equilibrium sample, its origin erased. Starting far enough back guarantees the memory of the initial state is already gone. The primitive is this. Do not estimate convergence, witness it by watching a random map collapse its whole state space down to a single point. This section explains variational methods, the trick that turns an intractable distribution into a tractable optimization. An intractable distribution yields once you stop trying to compute it and start bracketing it. You pick a tractable family, Q, parameterized by theta, the one number you cannot evaluate. The partition function z turns into the target of an optimization whose objective you can actually evaluate. Gibbs's inequality is the entire engine. Because the relative entropy from Q to P is greater than or equal to 0, the variational free energy splits exactly. Beta times the variational free energy, F tilde equals the relative entropy from Q to P, plus beta times the true free energy, F. So F tilde sits above the true free energy, so F tilde sits above the true phi F, with slack equal to how badly Q fits. Minimize over theta, and you tighten a certified bound. A lower bound on z drops out for free. The primitive is this. Replace an impossible sum by an optimization that carries its own guarantee. This section explains how an impossible computation becomes a solvable optimization. Intractability dissolves the same way every time. You cannot compute the true distribution, P, so you replace the search over P with a search over a parameterized family, Q of theta, one you can actually handle. You pay for the substitution in a currency that is provably non-negative. Here, that currency is the relative entropy, the Kullback-Leibler divergence between Q and P. Gibbs's inequality, the fact that this divergence is greater than or equal to 0, is the whole lever. The variational free energy splits exactly. Beta times F tilde equals the relative entropy between Q and P, plus beta times F. So minimizing it over theta drives Q toward P. And at the same time, it bounds the one quantity you actually wanted, the partition function z, from below. That is the chapter's role in the book. It turns sum over all states is impossible into optimize a tractable surrogate and keep a guarantee bound. This section explains why hidden sources can be pulled back out of their mixtures, and it turns on one fact: the sources must be non-Gaussian. That is the whole chapter in a single turn. The setup is this. The data X is a linear blend of independent latent signals, written as X equals G times S, and you want to invert the unknown mixing matrix G from the samples alone. Maximum likelihood on W, the inverse of G, gives you the learning rule. But the deeper constraint is a symmetry argument. A Gaussian prior on the sources is rotation invariant, so nothing in the data can favor any particular alignment of the latent axes, and G becomes unrecoverable. Heavier-tailed priors break that rotational symmetry and pin the sources down. The tanh nonlinearity is what encodes such a prior, the one whose density goes as what encodes such a prior, the one whose density goes as 1 over cosh. Independent component analysis is the simplest, continuous latent variable model. Independence together with non-Gaussianity is exactly what makes it identifiable. This part explains one shape that a whole family of models collapses into. Strip a model down to a single frame, and what you observe is manufactured from hidden causes you assume are independent, and inference runs that factory backwards. That single frame is X equals G times S, where the sources S are separably distributed. It subsumes mixture models, hidden Markov models, factor analysis, even error, correcting decoding. In decoding, the encoding matrix G is known, but here it must be inferred. Independent component analysis is the simplest, continuous instance. You recover the unmixing matrix W, the inverse of G, by maximum likelihood. Here is the chapter's pin, and it is understated. Independence alone cannot orient the axes because a Gaussian latent variable is rotation, invariant, so no evidence favors any alignment. Non-Gaussianity is the only thing that lets the sources be recovered at all. That constraint is the whole subject. This part shows how ignorance takes a definite shape, and why that shape is a symmetry. Ignorance has a shape, and the shape is a symmetry. Ask which digit an unknown physical constant starts with. You don't know its units, so your belief must survive multiplying x by any scale, an invariance under the multiplicative group. That single constraint forces the prior uniform on a logarithmic axis, and reading off the digit widths gives Benford's law. The probability of a leading digit d equals the base 10 logarithm of 1 plus 1 over d. Here is the surprise, stated flatly, from chapter 35. Ignorance does not correspond to a uniform probability distribution. The chapter is a rag bag by design, but every item runs one move. A prior is the fixed point of whatever transformation your ignorance cannot distinguish, never a flat default you reach for when you lack one. This section explains why ignorance always has a shape, and how symmetry draws that shape. The spine of the chapter, threading three unrelated puzzles, is that knowing nothing is never uniform. Whatever invariance you cannot break becomes your prior. Benford's law, in example 35.1, is the clean anchor. Ignorance of the units of x forces scale invariance, and scale invariance read on a logarithmic ruler already yields the result. The probability of a first digit d equals the base 10 logarithm of 1 plus 1 over d. The same move runs beneath the rest. The Rhea and Delbrück done by Bayes rather than by sampling. Theory hacks and causation read off data because a prior can encode assumptions instead of feigning none. Sampling theory discards this structure. Bayesian inference keeps it and extracts more than the orthodoxy admits is there. This section explains decision theory as the single move that turns belief into action. Belief never tells you what to do. A posterior, P of x given A, ranks worlds by plausibility. Acting needs a second, orthogonal object, a utility, U of x and A, pricing each world. Decision theory is the one move that fuses them. Choose the action that maximizes expected utility, the argument over A that maximizes expected utility, the argument over A that maximizes the integral of U of x given A. McKay calls this trivial. The entire content is one integral against the posterior, with inference doing all the hard work upstream. The generative byte is that preference and belief factor. Where utility is linear, the posterior spread cancels and you follow the mean alone, picking the action with the largest mean. Only curvature in U, or the prospect that new information might change which action you take, makes uncertainty worth paying for. This section explains why decision theory is the easy part and where that ease finally breaks. Everything hard about deciding lies upstream of the decision. McKay's thesis is deflationary. Given the posterior probability of x given A, which the whole book has taught you to compute, choosing is a one-line argmax of the expected utility given A. Decision theory is trivial, apart from computational details, just like playing chess. He writes in chapter 36, just like playing chess. He writes in chapter 36, here is the primitive. A decision layer is inference plus a payoff, weighted maximization. It inherits all its substance from the probability model beneath it and contributes only two things of its own, the utility function and the search. The chapter exists to bolt utilities onto the inference machinery, then to expose where the triviality breaks. That is the Tanzanite prospecting anchor, when acting now must anticipate information not yet gathered, folding forward probability and inverse probability into one tree.